Welcome to Study Loop.
Okay, our question says that at time t equals 0, a batter hits a baseball with an initial speed of 28 meters per second at an initial angle of 55 degrees to the horizontal. An outfielder is 85 meters from the batter at t equals 0 and as seen from home plate. The line of the sight of the outfielder makes an angle to the horizontal of 22 degrees with the plane in which the ball moves. See figure 64. What speed and direction must the fielder take to catch the ball at the same height from which it was struck? Give the angle with respect to the outfielder's line of sight of home plate. Okay, so I wrote down here a couple of things that we have. Well, the initial speed was 28 meters per second. The initial angle, which we're going to call theta naught, was 55 degrees. Okay. We're also told that the outfielder, let's rewrite this, that the outfielder is 85 meters from home plate. So I denote that over here, the 85 meters. Home plate, I'll draw a little red dot here. This is home towards the outfielder. And then R here is the range the outfielder would have to cover, okay? And X here, and this X here is the arrow that shows the direction in which the outfielder must run. Okay, so since the ball is being caught at the same height from which it was struck, we can use the range formula from example 3-10 to find the horizontal distance the ball travels, which is R there, that I denote as R. So let's go ahead and do that. Okay, so the range formula is R. Let's use black again. R is equal to the initial velocity, v naught, squared times the sine of 2 theta, okay, divided by gravity, okay? And maybe I should use different notation. We'll call this theta prime. Theta prime is that 22 degrees there. Okay, gravity is 9.8 meters per second on Earth. Okay, so we plug in all those values and we find that this equals 75.175 meters for the range. Okay, and that's then, as seen from above, the location of home plate and the point where the ball must be caught and the initial location of the outfielder are shown in the diagram there, right? The the arrow that I indicate as X, as I previously stated, is the length of the distance which the outfielder must run. And you can find this using the law of cosines as applied to a triangle. So we're going to find X using the law of cosines, where X is equal to the square root of, in general, it's a squared plus b squared plus 2ab cosine of the angle. That's in general. But for our situation, let's plug in those values. It's A is r squared plus 85 meters squared plus 2 times r times 85 times cosine. Here, let's put some parentheses around that 85 so you can tell that that's a multiplication. Good notation there. Times 85 times the cosine of the angle, and the angle in question here is the 22 degrees. Okay, and if you plug in for R, the 75.175 that we found before, you find that this X is equal to 32.048 meters. Okay, so now we found the distance that the outfielder must cover, and the angle theta at which the outfielder should run is found from the law of cosines. So now we're going to use the law of cosines, which says that the sine of the angle theta divided by x is equal to, this is the sine of the angle theta prime times x is equal to sine of the angle theta divided by r. So there's the laws of cosines. So now we want to solve for theta, because that's what we want to find. We know everything else. Theta is equal to the inverse sine of r divided by x times sine of theta prime. Okay, so if you plug in for r 75.175 meters, you plug in for x 32.048, and you multiply that ratio by the sine of 22 degrees, you will find that that comes out to equal 61.49 degrees. Okay, and since what we are actually trying to find is the average velocity of the outfielder, we can assume that the outfielder's time for running is the same as the time of the flight of the ball. The time of the flight of the ball is found from the horizontal motion of the ball at a constant velocity. So we know the ball is going to travel the, here, let's start a new page. We know the ball is going to travel the distance of the range, which is going to be equal to the velocity in the x direction times the time. Let's solve for time. That's what we want. Time is equal to the range divided by the velocity in the x direction. The velocity in the x direction is v naught times the cosine of theta naught. Okay, so if we plug in what we have on the previous page for the range, 75.175, for v naught, 28 meters per second, and for theta naught, 55 degrees, we find that the time is equal to 4.618 seconds. Okay, now that we have the time, we can find the average velocity, which is going to be equal to the distance, x, divided by the time. So this is the average velocity of the runner, and that is going to be, for x, you plug in 32.048 meters. For time, you plug in what we just found, 4.618 seconds. You find that this is equal to 6.8 meters per second as the average velocity of the outfielder. Okay. And then the angle that he ran, which we found, which was theta, is equal to 61.49 degrees relative to home plate. So we can box that in as the angle we were asked to find. Those are our solutions.